It's our pleasure today to have Professor Yunqin Zheng from the Kavli Institute for Theoretical Sciences at the University of Chinese Academy of Sciences give a talk. He will talk about non-invertible symmetries, boundaries, topological field theories, and applications. Please welcome.
All right. Thank you very much for the kind invitation. And it's a great pleasure to visit BIMSA. I hope I can visit more often in the next few years. Today I'm going to share with you a story about the non-invertible symmetries and its interplay with the boundaries and the topological field theories and the various applications of these ideas. This talk is based on two papers that recently we put on archive with two fantastic collaborators, Icho Choi, who is now in IAS, and Brandon Ryan, who is in Stony Brook right now. Okay, so although I'm going to talk about our work, but there are many intimately related works that appeared recently on archive, and this is the partial list of them. And if you're interested, please feel free to read all of them. And okay, so let me get into the motivations. So first of all, we are all taught that quantum field theory were specified by a set of the local operators and their correlation functions. So we saw that if we know all the local operators and if we somehow can compute all the correlation functions, then we claim success. However, the recent developments of quantum field theory says that this is far from enough. There are a lot of operators that are not the local operators. They are extended operators. Then they have interesting correlation functions and they have interesting RG flows on them. So, and there are two different theories who share the same spectrum of the local operators, but their extended operators are different. So which means that studying the extended operator is very important. So what are they? The examples are the line operators. For example, if you have a gauge theory, you have Wilson lines or Tooth lines. You have surface operator. For example, in QCD, we have observed the flux tubes. There you have boundary conditions. So if we can study different type of the boundary condition. If we put two theories together, we can study the interface and domain walls. And all of these lines are generically non-topological. But when these extended operators are topological, then the modern development tells us that we should think of these topological operators as the global symmetries. And it turns out that it's a very fruitful way of thinking about these topological extended operators. So, and it's also very interesting to study how the topological operators intertwine with the local and extended generically non-topological operators. And our talk is to illustrate this idea of how the topological operator, or namely how the global symmetries, interact with various local and extended operators. This talk is about the general symmetries on non-invertible symmetries, but before we start, let's first remind ourselves about what is the ordinary symmetries. And let's begin with the simplest case where we study the symmetries in 0+1D quantum mechanics. The quantum mechanics 101 tells us that if we have the Hamiltonian, then the symmetry is we claim that there is a symmetry of the Hamiltonian if we can find an operator U which commute with the Hamiltonian. So this is the basic definition of the symmetries. And suppose we find such a U, then we can first of all scale it by arbitrary complex number, and it still commutes the Hamiltonian, so it's still a symmetry. If we have two different U operators, then we can take any linear combination of them weighted by generic complex numbers. Then this combination is also a symmetry because it also commutes with the Hamiltonian. And in fact, it's well known that by Wigner, like a century ago, that the quantum mechanics, the symmetries are implemented by or classified by unitary or anti-unitary operators. In fact, if you have a Hamiltonian, actually you can find many unitary symmetries, and the number of symmetries is as many as its eigenvalues, because you can first diagonalize the Hamiltonian, you find the eigenenergy states, and then you can use the energy eigenstates to construct a unitary operator, which commute with the Hamiltonian by construction. So you have many symmetries, as many symmetries as the number of eigenvalues, eigenstates. So this somehow shows that the symmetry operator here, which can be generically non-unitary, is sort of equivalent to a unitary symmetry. Why? Because for arbitrary, like generic non-unitary operator, we can write in terms of this complete set of the unitary operator. So in some sense, the unitary symmetry and non-unitary symmetries are equivalent. So it means that well, we don't have to worry about non-unitary symmetries in quantum mechanics. However, the story is a little bit different in higher dimensional quantum field theories. The main reason is that in higher dimensional quantum field theories, we require locality. So, yes. Yes. Operator. Well, so there's a complex conjugation operator, and then you can multiply the complex conjugation operator to arbitrary unitary operator to get a. So, okay, so in 1+1D, first of all, how do we claim that there is a symmetry? So we again have a Hamiltonian, and we again require that the Hamiltonian commute with the operator. So if the operator commute with the Hamiltonian, then with this operator, well, if it's a symmetry, then it must commute with the Hamiltonian. But this is not the only requirement, which should be contrasted with the 0+1D quantum mechanics case. Also, because we have the space direction, so this U operator is now an extended operator. It acts on the full Hilbert space. So it's in particular, in 1+1D, it's a line operator. Now, here we put the line. So in the first bullet point, we consider the operator that acts on the Hilbert space. So this operator, this line is a space-like line. But now we can change the direction of this line and make it to be a time-like line. So this U operator, or this U operator can extend along the time. So this defines a defect Hilbert space, or it changes, inserting a U operator along the time changes the boundary condition. So it defines a defect Hilbert space. And these two interpretations of, or these two ways of dealing with the symmetry operators should be related, should be compatible with each other. Namely, we can view the time either in one direction or in the other direction. So in order to be consistent, so we have to require this modular invariant condition. And this modular invariant condition tells us that if we scale an operator U by arbitrary number, arbitrary complex number, then we should scale the change of the definition of the defect Hilbert space. But the defect Hilbert space should always have dimension 1. So we cannot rescale by arbitrary complex number. We can only rescale by an integer, or non-negative integer number. And so how do we find the symmetry? So we just try to solve this this modular invariant condition, and this is sort of a philosophy of bootstrapped symmetries. So as I said, that we cannot rescale a symmetry operator by arbitrary complex number. So which means that it can invalidates most of the the symmetry operators that we constructed for the quantum mechanics case, because for most of them, they do not admit a well-defined definite Hilbert space. So this tells us that in this case, the unitary symmetries and non-unitary symmetries are really inequivalent, because the argument that we applied in quantum mechanics cases fails. We cannot use these operators. We cannot use this operator and take arbitrary combination with a complex number coefficient. So in the dimension greater or equal than 1 + 1 dimensions, the symmetry so it makes sense. So the unitary symmetry and non-unitary symmetry are really inequivalent. So it makes sense to study them separately. But rather in the quantum mechanics case, they are kind of equivalent. So it's sufficient to study one of them. And as is classified by the Wigner, that it is sufficient to study the unitary symmetry or anti-unitary symmetries in quantum mechanics. But in higher dimensions, we should also study the non-unitary symmetries. Yeah, so these are the two different definitions. So not definition. These are the two different ways to use this operator U, and they have to be compatible with each other. Yes. Yeah. So in particular, the U commute with H determines that inserting U here or inserting U like somewhere else is does not matter. Yes. And in the when we are considering the theory, this fails to work. What's wrong? This one? This is a definite Hilbert space. Yes. So this is the time, this is the space, and you put a U operator here. So this is a definite Hilbert space. When you go around the space circle, then you should act upon by U. So it changes the boundary condition of your fields.
Those are twisted sectors.
Yes, those are twisted sector Hilbert space.
Can you be a little bit more explicit? Like I give you a state.
Yes.
And I put it on the circle.
Yes. Yes.
And the HU is the Hilbert space corresponding to the
state
where I glue the circle.
Yes, that's right. That's right. That's right. Yes.
Okay. So
yes. So suppose you have a spin model. So you have a circle and there are many sides. And each side is spanned by some spin variables up or down. And we define that Si plus L, where L is the number of sides, is equal to, is related to Si by some number. So this number is, so in the case of the Z2, so this is the, this is the, defines the boundary condition of the space. Yeah. Yeah. Right. Right.
So this can include
LSM anomaly is a different thing, right? This is just the boundary conditions. But this is a way to detect the LSM anomaly. Okay, so and in the Euclidean space-time, the space and time are equivalent. So more generally, we should think of this U as a topological operator, which commute with the Sturz energy tensor. So, okay. So here I reviewed how to find the symmetry for a given Hamiltonian. So namely, there's like a bootstrap way of finding the symmetries. And and then before talking about the non-unitary symmetries, let's first review. Yes. And so it's a modular bootstrap. So we just it's just solve some self-consistent relations. Yes, yes. This is the modular. This is what I mean by the modular invariance. Yeah. If you impose more conditions, like say the conformal bootstrap, then you impose conformal symmetry. But now we don't. Yes.
But why are you stressing that this you is the operator for only for the unit space-time for a real space-time?
Yes.
We cannot call it like that. It's not a project.
Well, at least I don't want yeah, let me not comment on that because I'm not quite confident. You should commute with the search energy tensor, no matter it's Euclidean or Minkowski.
Yeah.
So yeah, maybe in that sense it's total.
Hamilton doesn't know whether you're Euclidean or Minkowski. Yes.
Right. Okay. Okay. Yeah. All right. So let's remind ourselves that what can we in general say about the unitary symmetries. So first of all, the unitary symmetries are implemented by a unitary operator, and each unitary operator has an inverse, so it's also called an invertible symmetry. In the language that we use commonly nowadays, and these symmetries are classified by groups. By the way, in this talk, I'm going to focus on invertible finite symmetries. So there are a finite number of the group elements, and this group acts on the many things. Like I can act on the Hilbert space, states in the Hilbert space, or I can act on local operators or extended operators. And then because this group acts on, or symmetry acts on these operators, then the operators like form a so transform under this group, and we can organize them into different multiplets or different representations. So. Yes, for example, in a three-dimensional TQFT, you have the line operator, and the zero form can change the type of the line operator. This is one reason. Okay, so now for the non-unitary symmetries, we can still do almost similar things. So for non-unitary symmetries, now they are generically implemented by topological operators, but generically they do not admit an inverse. So usually we call them non-invertible symmetries. And the mathematical tool to describe this non-invertible symmetry, especially in the case when the symmetry is finite, is the fusion category. So they are classified by the fusion category C, in particular in 1+1D. And this fusion category symmetry also acts on various things, acts on the state in the Hilbert space, acts on local operators, extended operators. And we can organize all of these operators and states into different multiplets of the non-invertible symmetry C as well. And this talk is to make these statements more precise. Okay, so this is the outline of the talk. So first, I'm going to very briefly review the fusion category as non-invertible symmetry in 1+1D. And then I'll discuss how this fusion category symmetry C acts on the boundaries and boundary changing operators. And then I'm going to talk about the representation theory of these symmetries that acts on these boundary changing operators. And it turns out that the three-dimensional TQFT technique is a very useful tool to achieve this goal, to understand the representation of these symmetries. And then I'm going to mention several applications. So this is a list of the application. Okay, so this is the outline. Okay, so let me get into the first part, which is the brief overview of the fusion category. So the fusion category is like a category theory equipped with the fusion structure. And it has many objects. So it has the finite number of objects labeled by A, B, C abstractly. And they are associated with each line operator. So each line operator is labeled by an element in the object, like an object in the category. And the different line operators can fuse. So their fusion rule is like this. So if you take the two lines and put them on top of each other, then the whole thing can be decomposed into a direct sum of different lines. And the coefficient is like a non-negative integer. And these different lines, we can consider a web of the lines, and they can terminate on each other, for example. And if we deform the configuration of the web a little bit, then they are related by this crossing relation or F symbols. So, and these F symbols should satisfy certain consistency relation. And this consistency relation is very difficult to solve, but nevertheless, for a small number of the objects, then this consistency relation has been solved. And as a special case, the finite group is a special case of the fusion category symmetry. Fusion category, which is denoted as the fact of G omega, where omega is basically this F symbol, which characterizes the 't Hooft anomaly of the global symmetry G. Okay, so then when this like a fusion category admits a further structure, such as the braiding structure, then this category is called the modular tensor category. Wait. Okay. Yeah, I explained this already. So, and then there are many examples of the fusion categories. For example, the Ising fusion category. I think all of us are familiar with it. And we have the diagonal RCFTs, where the topological lines are the Felindy lines, and they also appear in the as the topological lines in the G level K transcendent theory. And also we have the orbifold CFT, where if we start with the CFT with G symmetry, G is a finite, possibly non-abelian symmetry. And if we get G, then we get the Rebound G symmetry. And when G is non-abelian, then Rebound G is a fusion category, which is not a group. For simplicity, I'm going to focus on conformal field theory in 1+1D in this talk. But some of the statements can be generalized to quantum field theories, generic quantum field theory that does not require conformal invariance. Okay. Now, okay, so this is the brief overview of global like non-invertible symmetries in 1+1D. Then let's talk about how these non-invertible symmetries act on various things. They can act on the boundary conditions, and they can act on like boundary changing operators as well. So let's first start with the boundary condition. So let me first briefly overview what is the conformal boundary condition and how do we find them. So the conformal boundary conditions are bootstrapped in a similar way as we bootstrap the symmetries. So we started with the imposing the condition that this boundary condition preserve half of the conformal symmetry. And then we also impose some self-consistency condition. For example, if you have two boundary states, so each boundary condition is associated with a boundary state, which is called a Carty state. And suppose we have two Carty states, so they can be interpreted as these two Carty states can define an interval Hilbert space. So we can consider this setup, and we can also consider this setup, and this time is a time, the space is a time, is a space, and in one situation we can consider the boundary states at the past and the future time slice, and in another setup we consider two boundaries. The space has two boundary conditions, so there are two boundary conditions. And these two boundary conditions define a Hilbert space on an interval, which is labeled by H sub BB prime. So these two interpretations or these two use of the boundary conditions should be consistent, compatible, and by modular invariance. So this is the modular invariance is usually called the Carty condition. So then we can solve this Carty condition and together with this like condition for preserving half of the conformal symmetry, and together with we impose on simpleness condition, and sometimes we can solve the set of the boundary states and the boundary conditions. In particular, when the CFT is a diagonal RCFT, then the boundary condition is uniquely determined and has been famously solved by Cardy in the late 90s, late 80s. Oh, okay. Yes. 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 So this B, that's right. They are the Cardy state, right? They so each state, so this Cardy state is a state defined on the Hilbert space, and by the state operator correspondence, it corresponds to a operator, local operator, and leave it on the bound. So suppose that we have a say, consider the boundary state like this. So you have, well, let me see. Yes, so these two boundary conditions by the state operator correspondence should, so this is a state in the Hilbert, in the interval Hilbert space, correspond to some operator living as the boundary changing operator between the two boundaries. Yes, so one boundary changing operator. Yeah. Okay. And so this is a brief overview of the states, conformal boundary conditions and the boundary states, Cardy state. And then let's talk about how the symmetries act on the Cardy state. So how does the symmetry act on Cardy states? So Cardy state is just some state on the S1 Hilbert space. So we can consider a symmetry operator wrapping around the space circle, and then fuse it with the boundary state.
Some superposition of the state in Hilbert space.
Yes, that's right.
With some coefficient.
With some coefficient. So
part of the Hilbert space.
Yes, this is a part of a Hilbert space, but the Cardy state is a very special set of the states. Right. They have to satisfy various constraints. Yes, so they preserve half of the conformal symmetry, and they also satisfy this modular invariant conditions, which is very constrained. For example, they cannot be, typically they are not normalized to 1, for example. Okay, so then if we have the state, if we have a symmetry operator, then we can act on the Cardy state. And the result is generically a non-simple Cardy state. So we can expand it into a sum of the Cardy state with the non-negative integer coefficient. There are 3 for icing. Yeah, there are 3 Cardy states. And the Cardy state for the diagonal RCFT is in 1-to-1 correspondence with the number with the primary operator, conformal primary operator.
It's almost like the number of the also is the same.
Yes. For diagonal RCFT, there are. That's right. Yes. Yeah. For non-diagonal, it's generally.
For non-diagonal, Cardy states also work out.
Yes. Well, that's right. There are scattered literatures on this, and
Also, as you say, level K, and they're very just a diagonal and non-diagonal state.
That's right.
If people work over the Cardy state for S2 level K.
I think that is kind of how it works.
I think it's worked out.
And I think
Mathematicians work it out. Okay.
Yes. Yeah.
But okay.
I seem to have
level.
You mean the ACU2 WZ model, right?
Right.
Yes.
Yes, yeah. Okay. Okay, so then, so suppose we consider two such operators, then like A and B, and we can study their algebras. And the algebra is nothing but just the ordinary fusion algebra of the diffusion category. So and the fusion like a algebra coefficient is just this NABC, non-negative integer. And so it means that these Cartier states form some representation of this fusion algebra. And this representation, because so it's basically this one. So each so the representation is given by this matrix, and because this matrix takes the non-negative integers, so this is called a non-negative integer representation, or NIMR for short. Then the question is, how do we like understand this non-negative integer representation more concretely, or how do we label, how do we count the non-negative integer representation? So this is the one of the question. And in order to solve this question, it turns out that the three-dimensional TQFT is a very useful tool to study this problem, to study the representation theory of the global symmetries and that acts on the boundary conditions, for example. Well, I have to mention that the representations, you people have already used the three-dimensional TQFT to study the representation theory of how the symmetries act on the local operators. So, or on the states on the circle. And then for this talk, I'm going to study some other, also how the symmetries act on the boundary conditions or boundary changing operators. So this is, we should not feel too surprised about that, because the three-dimensional TQFT has already been proven to be very useful in a intimately related. No, so this coefficient and this coefficient are different. This coefficient is the fusion of two symmetry operators, A and B. But this coefficient is the fusion A with the boundary state. So more abstractly, each boundary condition or boundary states are characterized by the module category of the fusion category. So this coefficient specifies the fusion coefficient in the module category, not in the fusion category itself. Module category of the fusion category.
But I think that this in this partial T, this field,
yes,
isn't module
no. So module category, not modular category. Yes. Yes. Okay. Okay. So before talking about how useful the three-dimensional TQFT is for the purpose of studying the representation theory of this NIMREP. So how the symmetry operator acts on the boundary conditions. Let's briefly review, using a one-slide review of what is the three-dimensional TQFT and why we care about this. So I think most of you know what this is. So this is called a symmetry TFT in some community, but in other community, people call them like topological holography, or call them symmetry topological order. There are many names, but they refer to the similar things. So what is it? So if suppose that we have a two-dimensional quantum field theory, and then let's call it label the theory by Q. And then this Q, suppose that we have a symmetry. So it has certain symmetry, which is described by the fusion category C. So this is a symmetry operator that lives that we can turn on for this two-dimensional quantum field theory. And then the idea of this symmetry TFT construction, or the sandwich construction, is that we can blow up this two-dimensional theory into a 2 + 1 dimensional slab, where in the middle of the slab, we have a 3-dimensional topological quantum field theory, which is described by the dream field center for the input fusion category C. And this TQFT is called the trivial TQFT for the fusion category C. Or in the condensed matter literature, it's also called the Levin-Wen string net model on the lattice, or the Degrave-Witten model when this C is invertible. And there are two boundary conditions of this 3-dimensional TQFT. So the left boundary condition is a topological boundary condition. And in this case, we choose the Dirichlet boundary condition. So here it's blocked, but it's labeled by B reg, where reg denotes the regular module category of the fusion category. See? And the symmetry operator, so the nice, and the right boundary is the dynamical boundary. The nice thing about this construction is that the topological operator, or more generally, the universal or RG invariant informations related to symmetries and anomalies are all decoupled from the dynamics, where all the dynamics are located on the right boundary condition, but all the kinematic universal and kinematic informations are decoupled into the bulk and onto the left boundary. In particular, the global symmetry C, the symmetry operator for the global symmetry C are only supported on the left boundary. So it's just some boundary condition, which is not topological. So we have a 3-dimensional TQFT, and we can consider its boundary conditions, right? Or boundary states. Yes. So let's consider a simpler situation where the symmetry is a group, for example, and then the thing in the middle is just, so suppose the group is G, then the topological theory in the middle is just some G gauge theory. And then the dynamical boundary condition is just specified by a boundary state, which is given by this form. Q, A. Where A is the gauge field, the G gauge field. And the coefficient, and this A cat is some like a basis state for the configuration, specifying the configurations of the gauge field. So this is just some basis state, and the coefficient encodes all the dynamical information, which is given by the partition function of this theory, 2D theory Q. So this encodes all the dynamical information, and in particular, it can flow on RG. Okay, so this is it. Okay, then let's consider how to incorporate the boundary conditions in this setup. So now we start with a 2D theory, but with a boundary condition. And then we still blow it up into a 2 + 1 dimensional slab, where now the boundary condition is still also separates into a triplet. So you have a so this thing is a topological boundary condition of the 2 + 1 dimensional symmetry TFT, and this blue line is the topological line between the two topological boundary conditions, a B reg and the B boundary. And this is some non-topological boundary conditions, which encodes the dynamical information of this non-topological boundary condition of the 2-dimensional QFT.
So from what I understand, the B reg on the left,
yes,
but there it's gapped, right?
Yes, it's gapped and it's a Dirichlet boundary condition.
So it's like they're finding some simple logic.
Yes.
Of C, basically.
Yes, yes.
And so my question is this E boundary, like
yes. It's also gapped, but it does not have to coincide with B reg. So the different choice of the B boundary are determined by the property of the boundary conditions. That's right. Right. That's right. And yeah, it's generically gapless. So if this boundary condition is gapless, then this boundary changing operator is also gapless.
Oh, like, is there a categorical description of B tilde?
No, it's in general very depends on dynamical details. So yeah, sure. Okay, so the nice thing about this construction is as follows. So remember that all the symmetry operators are live on the left boundary. So now we can think about how the symmetry operator acts on the boundary condition. Before we said that if we fuse the symmetry operator with the boundary condition, then it can decompose into some direct sum with the non-negative integers. Now similar thing here. So if we have the symmetry operator and if we fuse with the boundary condition, then we can only change this topological boundary changing line. We cannot change this surface. We cannot change this boundary condition, B boundary. So which means that this B boundary is invariant under the action of the symmetry operator, where we parallel fuse the symmetry operator with the boundary condition. So it means that this B boundary give us a label for different representations of different NIM-reps. So, or in other words, B boundary, so it's in one-to-one correspondence. It's a label for the NIM-rep for the boundary conditions under the action of the non-invertible symmetry. Okay. So this is a brief summary of what we have been discussed so far. So we consider the boundary conditions, and the boundary condition is acted upon by the symmetry by parallel fusion. And the different symmetry operators satisfy the fusion algebra. And the boundary condition forms a NIM-rep under this fusion algebra. And this NIM-rep is in one-to-one correspondence with this gapped boundary condition or topological boundary condition in the symmetry TFT setup. Okay. Now, so far, we only discussed the one boundary, but how about two boundaries? So relatedly, we can discuss the interval. So we can consider this picture where we have an interval and have two boundary conditions. So B and B prime. Yeah. No, it's for generic. It's for generic. Yeah. Okay, so we have two boundary conditions, so B1 and B2, and they define an interval Hilbert space. And then we can consider how the symmetry operators act on this interval Hilbert space. Namely, so suppose we have two boundaries, then we can consider a symmetry operator that acts on the interval Hilbert space. But generically, this symmetry operator, if we want to move this symmetry operator up and down, and which is required if we want to fuse the symmetry operator with the boundary conditions, then we need to require that this junction is topological. But if we require this topological, then typically, if you impose C1 and B1 are the same, then there's generally no topological junction between them. So in other words, in general, the symmetries will change the one Hilbert space, which is labeled by B1 and B2, to another interval Hilbert space, which is labeled by C1 and C2. So in this case, we cannot put the periodic boundary conditions. But so it means that if you want to study the symmetry operator that acts on the interval Hilbert space and impose the periodic boundary condition, we'd better consider a situation where there is a topological junction between that between the B1 and the B1 and the A. So which means that this symmetry operator, this boundary condition preserves the symmetries, preserves the symmetry. And more precisely, it is called that the boundary condition is weakly symmetric under the fusion category. Okay. And if we consider state operator correspondence, then this interval Hilbert space setup is mapped to this boundary changing operator setup, where each state on the interval Hilbert space is mapped to a boundary changing operator O. And the symmetry operator acts in like this, like a semicircle, and the action on the boundary changing operator just amounts to shrink this semicircle, and which will produce another operator, boundary changing operator. Okay. Now, as we discussed, so for the boundary case, we discussed that we can consider algebra between the two operators that act on the boundary. But here, the situation is more complicated because each operator not only depends on like the label, but also depends on the choice of the junctions. So the algebra between such operator on the interval is more complicated. And the algebra, but nevertheless, one can explicitly work out this algebra using various like moves, topological moves. And suppose that this operator, A by 1 by 2, is called this H with many indices, which is like this. Then we can consider their multiplication rule or the algebras. And we find this complicated algebra. And this complicated algebra generically depends on the F symbols and the various quantum dimensions. And if you compute these coefficients, in general, there will not be integers. And they can not only be non-integers, can also be negative. So it's quite generic thing. So in general, they are valued in C, complex number. Okay. And this algebra, so this multiplication rule is called, so it forms out. So each operator, so this is an operator. Yes, and this operator, and we can consider the fusion of the two operators, and they can act on the Hilbert space.
Also, this operator,
Yeah.
operator.
Yes.
act on the-
Yes, and yeah, so this is the fusion of this operator, and so this operator form an algebra, and this algebra is called a boundary tube algebra in our paper, but in some other papers, it's called the annulus algebra or strip algebra. So they have various names. And then once we have this algebra, then we can consider the representation, like how the symmetries transforms. So the symmetries, so the boundary changing operator, the states on the interval Hilbert space, form a representation of this algebra. And we should consider like what is the representation? How do we understand, or how do we classify or count or label the representation of this complicated boundary tube algebra? So this is the task.
Like it's only really the two algebra when you like glue those guys, right?
So you mean
this fusion is stacking two of those basically.
the
Like
fusion,
pictorially. Like,
this one?
Yeah, that picture. You
Yes.
Two alone.
That's right. That's right.
So you get two when you like identify.
Yeah. So that's the ordinary tube algebra.
Yeah.
But here it's a different than tube algebra, and we call the boundary tube algebra. So it's basically like a square root of that. Yeah.
This case is A is symmetry.
Yeah, A labels the symmetry operator. Yeah.
So this is the whole, would I see what kind of this symmetry landscape are preserved from the, so each of the operator you wrote there is just it's already a good operator in the is a good boundary operator which has a symmetry attached.
Sorry, so can you say again? Which operator? Which operator? H is this, or like if you do the data operator correspondence. So H is like this semicircle thing, right? Y1, Y2. And we can consider two such operators, A prime, Y1 prime, Y2 prime, and we just consider their multiplication rule. Yes, like we can make it like this, and then shrink this bubble.
Yeah.
So yeah. Okay, so and shrinking this bubble requires some F move. So okay. So as you may already anticipated that in order to understand the representation of this complicated boundary tube algebra, we have to go to the three-dimensional symmetry TFT setup. I'm not claiming that it's the unique way, but it's like it's a very convenient way to think about this problem. So I have explained how to think about the boundary conditions in the symmetry TFT setup. And now we have two boundary conditions, and there's a boundary changing operator in the middle. So we can still do similar things. So each boundary condition is split into a triplet. And then the boundary changing operator also splits into a triplet. And then the boundary tube, so the symmetries act on the boundary tube algebra like this. So you have a semicircle operator and it can shrink over this boundary changing operator. And in the symmetry TFT setup, you also have this semicircle which lives on this B reg and then shrink it over. But again, shrinking it over to this junction only changes this junction, but it does not change this line, which is labeled by rho. So it means that this rho labels the representation of this boundary tube algebra. Okay. So as you can see that although the boundary tube algebra is very complicated, like this, but the representation is very simple. It's just in one-to-one correspondence with this rho, and because given us sim TFT, given a three-dimensional TQFT, one can classify its boundary conditions, and therefore one can also classify its the interface between the two topological boundary conditions. Okay, so this is also a summary of what we have discussed. So we consider the boundary changing operator, and the boundary changing operator is acting upon by the boundary lasso action, which is this semicircle thing. And then the different composing the two semicircle operator will satisfy this boundary tube algebra. And the representation of the boundary tube algebra is in one-to-one correspondence with some topological interfaces in the symmetry TFT setup. Okay. So this is let me see the time. Okay, so this is the general thing, and then let's consider some applications of the machinery that we have been discussed so far. So there are four applications, but they are kind of related to each other. So the first application is about the selection rule. So usually when we have a global symmetry, so what do we mean by the selection rule? Selection rule just means that if you have a correlation functions of local operators, then the correlation function vanishes if the sum of the charge of the local operators are not zero, right? So this is the selection rule. And for the generic, like for the non-invertible fusion category symmetries, then we can also do this, consider a similar thing. First of all, let's consider the case without a boundary. Then we can also consider some set of the local operators. And each operator is labeled carries some charge under the global symmetry, fusion category symmetry, and as you can anticipated that the charge is in one-to-one correspondence with the anyons that connects with the operator of Hilbert. So the representation is one-to-one correspondence with the anyons that's in the symmetry TFT setup. And the selection rule is just that if the fusion product of these anyons does not contain an identity channel, then this correlation function must vanish. So this is the selection rule without the boundary. But with boundary, one can immediately generalize this idea that so we can also consider some local operator that lives on the boundary or some boundary changing operator lives at the junction of the two boundaries. And then we not only consider the fusion of product of all the anyons in the bulk, but also some row operators that we have already discussed here. So we can consider the fusion product of both the topological line operators in the bulk and on the boundaries. And if their fusion product does not contain the identity, also consider J does not contain the identity, then the correlation function must vanish. So this is a very straightforward generalization of the selection rule for the non-invertible symmetries, even in the presence of the boundaries. Then the second application is about the validity formula. So this is not something that we anticipated, but it turns out that the validity formula somehow shows up in the discussion. So let's consider, first of all, let's consider the setup where we consider Hilbert space on the interval. And in the symmetry TFT setup, so because the Hilbert space is in one-to-one correspondence with the boundary changing operator, and in this symmetry TFT setup, this boundary changing operator splits into like the triplet, and this O operator, so this topological junction lives in the space which we call W. So O is this boundary changing operator lives on the Hilbert space of the two boundaries B1 and B2. And on the other hand, the symmetry TFT tells us that this O splits into O underline rho and O tilde, where O underlines a topological junction operator, and it lives on the space, which we call the W B1 B2 rho, which is living as a junction of the three topological line operators, B1 underline, B2 underline, and rho. And this O tilde also lives at the junction of the three line operators, but two of them are generically non-topological. So B1 tilde, B2 tilde, and rho. So it tells us that this Hilbert space decomposes into some of this, the sum of the product of these two Hilbert spaces. And this Hilbert space is topological because it's an intersection of three topological lines, but this part is non-topological. So it gives us some like a decomposition of the Hilbert space. Now, we can consider the trace over this topological Hilbert space with the insertion of this elements in the symmetry acting on the interval Hilbert space. So this is like a generalization, direct generalization of the characters, right? Group characters. So remember for the ordinary group character, this is labeled by, replaced by a group element, and this is the some Hilbert space. And we consider the trace. Now, if we do the conformal transfer, so if we do the state operator map, we can conformally map this configuration into this configuration, where we have a solid torus, and these three lines are mapped to these three circles. And this A, which connects these two boundaries, will now connect these two circles. But everything here is topological, so we can use various topological moves to evaluate this number. And it turns out that the end result is like this, where psi is some symbol, which is basically square root of the modular S matrix. But anyway, one can define what's so-called half-linking numbers. And using this definition, then we can express this configuration into some combination of the half-linking numbers. Yes. That's right. Yes. 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 It is dropped out. Yes. But the character only labeled only encodes this topological part, right? Character is just this particular character. Yes. Oh, I'm not talking about the conformal character.
No.
Yeah.
They wouldn't arise in that. Like sorry, this S here, that's denominator.
Yes, this one. This is the let me recall. This is the S matrix for in the bulk in the
internal. Yeah.
Yes. Yes. Yes.
Also take trace of the V.
Take the trace. Yeah, we can take the trace of the V, but I mean, for the purpose of deriving this Valenti formula, I want to only consider the trace of it. Yes. Right. Right. And so this is the result. But on the other hand, if we take A to be trivial, take A to be identity, then this figure, although it's of this complicated form, but can be evaluated alternatively by just parallelly fusing the three circles. And it will give us some non-negative integers, which is the dimension of some Hilbert space, dimension of this W Hilbert space. So if we take A to be 1, then the left-hand side, which is the character, which is just some integers fusion, which describes the fusion coefficient of the three loops. But on the right-hand side, we have this complicated form, which is the product of the half-linking numbers. So this is very similar to the Valenti formula. And in fact, it can be reduced to the ordinary Valenti formula if we take C to be MTC, modular tensor graph. Yes. 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 And then yes. And then take these two boundary conditions to be the B rect, and then it reduces to the ordinary Valenti formula. Okay, so so this is one application. The second the third application is that one can consider a refined version of the Afler-Ludwig-Carty formula. So let me explain what is the ordinary Afler-Ludwig-Carty. Later I'll talk about entanglement, but for now I'm just talking about the partition functions. Yeah, that's right. So for the ordinary Afler-Ludwig-Carty formula, so first of all, the Carty discussed so we consider partition function of the 2D CFT at high temperature. In ordinary, so in the 86 maybe, the Carty considered the torus partition function. Oh yes. So Cardi considered a torus partition function, but later Alpha and Ludwig considered the annulus partition function. So now let's consider the annulus partition function, but let's call them the after Ludwig Cardi formula. And if we consider this partition function at a high temperature, and then it turns out that the partition function is very universal. It's universally controlled. The leading contribution is universally controlled by the central charge of the CFT, and also together with the boundary G functions, G1 and G2. So this is the Cardi formula. Now, after the Ludwig Cardi formula. Now, here, if we have the symmetry, then we can refine this formula by asking, like, we don't trace over the full Hilbert space, but trace over only a specific sector of the Hilbert space. And this sector is labeled by representation. And we already know what is the representation, which is in one-to-one correspondence with some boundary changing operator in the symmetry TFT setup. So, and anyway, one can define this sub-Hilbert space using the symmetry TFT technique. And one can still ask, like, if we trace over this sub-Hilbert space, then whether we can get some more refined version of this formula. So as we already discussed that we already know what this rho is in the symmetry TFT setup, and then we can discuss the projector that goes from the full Hilbert space to this sub-Hilbert space. Sorry, this is a typo. Yes, the other way around. And I'm not going to explain the details, but the projector can also be worked out using this symmetry TFT construction, and it takes this complicated form. It also depends on these various half-linking numbers, and it's a linear combination of these line operators that act on the interval Hilbert space. Okay, so once we have this projector, then we can substitute it into the partition function. And then this is the partition function. We will trace only over this sub-Hilbert space, which is equivalent to tracing of the entire Hilbert space, but with a projector inserted. And if we substitute the formula for the projector, we'll get this formula. And then we use the standard trick by the Alpha and Ludwig and Cardi, which is to use the modular transformation to extract the leading order at a high temperature, and it will give us this contribution. And then we use the generalized Felingi formula that we discussed in the previous slide to simplify this formula. And so this is the generalized Felingi formula, and it turns out the final result is like this, where the last pieces are the ordinary formulas, but the additional piece here in the front are the new contributions that comes from the symmetry resolution. Okay, so this is this is called the symmetry resolved after Ludwig Cardi formula. And finally, there's a direct application of this symmetry resolved after Ludwig Cardi formula, which is that it can immediately give us the symmetry resolved in time entropy. So the symmetry resolved in time entropy is related to the partition function of the CFT on the cylinder in this particular form. And the reason that they are related to each other is that it is due to the fact that the geometry that we compute in time entropy is conformally related to the geometry of the cylinder partition function. Anyway, so one can one can use the results that we already get for the high asymptotic behavior of the partition function at a high temperature to compute the time entropy. And the leading contribution is like this. And by the way, the high temperature limit corresponds to this length is much larger than this circle. and by conformal transformation, it's mapped to the geometry where this length, the interval length, is much higher, much larger than the regularization size of the entanglement cut. So this is a nice, so this just precisely corresponds to the leading contributions of the entanglement entropy, where we indeed find that the leading contribution is proportional central charge, but there are sub-leading contributions, which are the boundary G functions, so boundary entropy, boundary G entropy, boundary entropy, and together with the new contribution that comes from the symmetry resolution. Okay, so this is a summary. So I discussed the non-invertible symmetry, and I explained that it's meaningful, which should be compared to the quantum mechanics case where it's not quite meaningful to discuss non-invertible symmetry separately. And then I discussed how the non-invertible symmetries that acts on various things, and discussed the representation theory, and I discussed the TQFT, which is a useful tool to understand the representation theory of these symmetries. And I discussed the several applications. And there are several obvious future direction, which is one is to generalize everything to high dimension, which I think is still very challenging, but it's more and more approachable. And another direction is to understand lattice realizations. Okay, so thank you very much.
And thank you for the wonderful talk. Are there any questions?
Yes.
You have to the boundary conditions, which is constant with it. Then you have to the fusion algebra, boundary fusion algebra, symmetric, and then you reach to 3D symmetric, which is very more how to read most symmetrically.
Yes.
So to get any additional, I would say, pentagonal that's what algebra is boundary. Do you have something more information? New coefficient or?
Sorry. So
then you have a fusion algebra with boundary conditions.
Yes.
Of the symmetric. Is there additional parameters than what you?
That's right. So the fusion, the algebra is more complicated, right? It depends on the choice of the junctions, and it also depends on this F symbols. And this F symbol is not the F symbol in the fusion category, but the F symbol involving the boundaries. So it's the F symbol. Yes, which involves the mod. Yes, this is F symbol in the module category. But the nice thing is that when the fusion category is itself a modular tensor category, then many things are computable. So this F tilde is computable. It's actually the same as if you consider the regular boundary condition, then it's the same as the bulk F symbol. And also the half linking numbers are also computable in that case. It can be directly related to written in terms of the bulk F and R symbols. So it's in the case of the modular tensor category, everything becomes a little bit simpler. But I agree that in general, say the various symbols that I wrote down, for example, this half linking numbers, they are not known except a few examples which are known in the literature. But generically, they are not known. But it will be But the formula is nevertheless correct.
So if in the, let's go back to the character formula, the formula that you have to
Yes.
the character. B1, B2, they're both underlined. Okay, right. So you're only tracing over the topological sector.
Yes,
So,
yeah.
but if let's say I pick on the right hand side also the topological sector, can you recover the usual character for the tube algebra? Because we know representations of like the actual tube algebra, right? It's just the Turnhout center.
Yes,
Would you
yes,
be able to recover?
yes,
that?
yes. Yeah, I haven't checked, but I think yeah, it's
Okay.
doable,
Okay.
and it should be true.
Yeah, because I'm interested in like these half linking numbers, like these
Uh-huh,
variants.
uh-huh.
Then as you said, like what you have here should be like the
Right,
square root of something.
right,
or
right,
Turnhout
right,
center.
right, right.
Yeah. And because like from just the purely mathematical point of view, there are certain cases where the Turnhout center, let's say it's like non-degenerate and pre-modular, let's say, then you can split up the Turnhout center into C out. So I'm wondering the half linking is kind of like, well, I don't know. It's giving some structure to one of the pieces of C, or maybe this is doing exactly that. Like maybe this is like doing that splitting of the Turnhout center. I don't know, but it would be interesting to kind of see that from just.
I see.
Is it there? Yes.
I mean, like making this was like to each of this thing.
Exactly.
Regarding this, I think regarding the entanglement when with the cardinal this canonical I mean ALC from I think if we go for the reason contribution is almost canonical, but
Entanglement?
yeah. Yeah. Yeah, here.
This one, yeah.
So this exactly characteristic of the fusion to tube algebra is the last term, right?
Yes.
Yeah. So is there additional meaning that it is contributing to this entanglement entropy because the rest is like canonically established and you can start the flows of the G functions and so on.
Yes.
But do you get any intuition on this term? Does it provide like?
This is just some how to say it, some subset. So this is like a topological entanglement entropy.
Yeah, that's what I'm saying. If the it's topological contribution.
It's a topological contribution, and it's very similar to the topological entanglement entropy in one higher dimension. So in 2 plus 1D, we consider TQFT, and we consider entanglement entropy. Then sometimes we can get the constant subleading term, which is the topological entanglement entropy.
Right.
And people can use various like surgeries to extract, like consider various combinations of the entanglement surface to extract the topological entanglement entropy.
Yeah, that's what I see. There is probably no other like topological interpretation of the changes. So like it is in the other terms. I see.
Yeah. So
because conceptually of the fusion algebraic characteristics.
The only intuition I have here is that here we are restricted to a particular symmetry sector. So we are in a more ordered situation. So the entanglement is lower, and the amount which is lowered is precisely this. This is a negative number.
Yeah.
So it's just because, so this piece is just because we are restricted to certain symmetry sector, some representation sector.
Sure, yes.
Yes. But maybe
probably we can see this in more general sense, but in particular, this symmetric constraining, you can see different behavior of the term with respect to which symmetric sector constraint.
Which symmetry?
Yeah, because like you say, you localize to certain symmetries, right? And this in the middle, so it is characteristics of this.
Right. Yeah.
That's probably the only mean. Yeah, I also see.
Yeah. So far, that's the thing I can say. That's So the last
No,
piece reduces.
that I also see. Yeah, I was thinking if there is something in addition that this topological restriction, I mean, construction is providing in additional interpretation of this additional.
Are you saying that's a? So what kind of answer do you want? You are trying to look for an answer where the last piece implies some
I don't think so.
topological
I
sector
think,
of
yeah,
the theory.
it's probably that much as it does, like you said. Yeah, I don't think. At least
It's related to the symmetry. It's the presence of last term is only because we're restricting the symmetry. So so in this sense, it's kind of different from the topological entanglement entropy, where the presence of topological entanglement tells us that there is some topological order in the bulk. But in this case, it's it's not about the topological order.
No, there is no such interpretation like coming from the bulk. It's just from the pure this topological junction construction.
Yeah.
Do you have any candidate for this discretization? Or?
Discretization. Yeah. We haven't studied it, but there are like a few other papers.
Can be like you understand, like categorizing this TVC, but a discretized version. This is what we mean.
You mean write the CFT on the lattice and compute the entanglement entropy?
Similar, yeah.
Similar. Yes. There are some papers discussing this, and they use they numerically verify the subleading piece. But I didn't do the numerical computation, but I think it would be interesting.
Yeah, what I see.
Any more questions?
Just a more practical question for this symmetry TFT construction. So on your topological boundary size, so on top of that, you also have to somehow decorate your topological boundary condition with this to also specify the same B1, B2.
Yes.
On this topological boundary. Are these always compatible? I mean, for concrete, because on the one side you have dynamical theory, right? And in the dynamic theory, you can find all the possible topological boundary conditions.
Yes.
And all the possible boundary conditions.
Yes.
But when you put it in the same TFT, so is whatever. So is this topological boundary condition always exist for previous center or?
Let me think.
From my side, it's like topological boundary is very new, and we also decorated your topological boundary condition on top of that with some.
Yeah, so you are asking like if we have arbitrary two topological boundary conditions of the TQFT, and we put them on next to each other, do they always admit the topological line changing operator?
Yes.
Yeah, I think so. And this topological line changing operator is so each topological boundary condition is described by some module categories in one-to-one correspondence with the module categories, right? So okay, so yes, so maybe we can say this. So B reg is has some symmetry C, right?
Yeah.
But if we have some other boundary conditions, then it turns out that the other boundary condition is always related to this by gauging some algebra. So you can have, for example, you can from this construction, you already know that there is a topological line or topological interface between these two boundary conditions, because you can just gauge on half space with boundary condition imposed. And then it's not very hard to convince yourself that if you have two generic boundary conditions, B1 and B2, and this correspond to C of A, module category C of A and C of A2, then this boundary condition is obtained by, like, you can ungauge one and then further ungauge A1 and then gauge A2. So there's always a topological interface between them.
Okay. Then you can just use that to find these limitations.
Yes. Yes. Yes.
Like with the boundaries, like one topological and one is dynamical. This thing, I'm just thinking on the analogy with consignment for each consignment where you can introduce the packets. Facts, and obtain like a discretized version of this, like to say like this. So like specialize it in a lot of this, but you don't know what's maybe
So your questions about what about the lattice realization of the dream field center of this trivial? But this is no, right? So this is the string net model. The string, the level one or string domain. Level one or string net model. Where so this gives you the Hamiltonian, and whose ground state is, so the ground state on the torus is in one-to-one correspondence with the topological operators in your TQFT. So there is a lattice realization.
Your computations you would be able to obtain analysis of variables like entanglement or coupling numbers. They would be exactly.
Yeah, the half-linking number was, I'm also not completely sure, but the half-linking number, at least some simplified version, has already been discussed in one of Levin's paper on the lattice in the context of the lattice model. So I think it's possible for the particular case. Yeah.
There is this notion of, like I'm saying, with this TQFT discretization, which from the physical perspective, would they happen to different
Any more questions? If there are no more questions, let's end the speaker again.
Thank you very much.